Somewhere in the depths of space, hidden behind a curtain of infrared light, something is happening that scientists did not expect to see. Not a monster, not an alien signal, something far stranger. A telescope built to look back toward the beginning of time has found objects. So small, so violent, and so impossibly out of place that they are quietly unsettling some of the smartest astronomers on the planet. And this month, that unease reached a new peak. Because the James Webb Space Telescope did not just find another pretty picture of the cosmos. It found evidence that parts of our universe may be behaving in a way our physics cannot fully explain. That is why headlines are calling this moment the point where Webb scared the world. Not because anything is coming for Earth, but because our entire model of how the universe was built may have a crack running through it. Let's back up for a second. Because to understand why this is such a big deal, you need to understand what Webb was actually built to do. Since it began full science operations in the summer of 2022, the James Webb Space Telescope has spent its time doing one very specific job, staring into the deepest, faintest corners of the sky and collecting light that has been traveling toward us for over 13 billion years. That is not an exaggeration. Some of the galaxies Webb has photographed sent their light out before the sun, before Earth, before almost everything in our solar system existed. Webb is, in the truest sense, a time machine. Every image it takes is a photograph of the past. And for the first few years, that time machine mostly confirmed what scientists expected. Sure, there were surprises, distant galaxies, strange colors, new exoplanet atmospheres, but the broad picture of cosmology held together. Then Webb started looking closer at a strange population of tiny, red, impossibly bright objects buried in its deepest images. Astronomers nicknamed them little red dots. And what they represent has become one of the most contested, most talked about mysteries in modern astrophysics. Here's the problem. These little red dots showed up in numbers far greater than anyone predicted. They are compact, some smaller than a third of a light year across, according to research published earlier this year, yet they shine with the brightness of hundreds of billions of suns. To put that in perspective, the distance from our sun to the next nearest star, Proxima Centauri, is over 4 light years. So imagine squeezing the light output of an entire galaxy into a space smaller than the gap between two neighboring stars. That is not supposed to be possible if these objects were made of ordinary stars, packed together. If they were, researchers have said, they would be the densest galaxies in the known universe. So if they are not just stars, what are they? This is where things get genuinely disturbing for people who study the early universe for a living, because the leading explanation now points to something almost too dramatic to believe. Baby supermassive black holes feeding on gas at rates that should be physically forbidden. In a study posted earlier this year, researchers proposed that these little red dots are black holes caught in rare, violent feeding episodes, growing at more than 10 times the theoretical maximum rate scientists thought was possible. This is called super Eddington accretion, and it means a black hole devouring far more material, far faster, than the laws of radiation pressure are supposed to allow. Now here is the part that should give you chills. If that model is correct, these little red dots are only the visible tip of something much larger. The same research suggests there could be an entire hidden population of these violently growing black holes sitting just below Webb's ability to detect them. In other words, the ones we can see may just be the loud ones. The rest could be feeding in the dark, completely invisible to us, scattered throughout the early universe in numbers we cannot yet count. Other teams have proposed different explanations entirely. Researchers at the University of Copenhagen's Cosmic Dawn Center concluded these red dots are black holes about 100 times less massive than earlier estimates, wrapped in a dense cocoon of gas that they are actively consuming, producing intense heat that leaks out as the red glow Webb detects. Meanwhile, a separate team argued for something called direct collapse black holes, where massive black hole seeds form almost instantly from collapsing gas clouds rather than being built, up slowly, star by star. Even scientists at Harvard have floated the idea that some of these red dots might not be black holes at all, but a completely new category of object. Gigantic, short-lived primordial stars, unlike anything that exists in today's universe. 3 competing theories. 3 different pictures of how the early universe actually worked. And every single one of them, if confirmed, forces us to rewrite a chapter of cosmic history we thought we already understood. So how did we get here? How did a handful of tiny red smudges in Webb's deepest images turn into one of the most urgent debates in modern astronomy? To understand that, we need to go back to where this story really begins, with a single patch of sky that scientists thought they had already fully explored. To understand why little red dots are so shocking, you have to understand what astronomers expected to find when they pointed Webb toward the earliest galaxies in the universe. For decades, the standard model of cosmology, often called lambda CDM, gave scientists a fairly clear timeline. After the Big Bang, the universe was dark and mostly gas. It took hundreds of millions of years for gravity to slowly pull that gas together into the first stars, then the first small galaxies, then eventually the larger, more structured galaxies we see around us today. It was supposed to be a gradual, patient process. Slow assembly, slow growth, nothing overnight. Then Webb looked back further than any telescope in history had managed before, and what it found broke that timeline almost immediately. Within its first year of full operation, Webb identified galaxies that had already formed within just 300 to 500 million years after the Big Bang, and they were not small, faint, struggling protogalaxies. Some of them looked mature, structured, massive, far larger than the standard model said they had any right to be at that age. Astronomers started calling them, only half-jokingly, universe breakers. The scientific community began referring to the whole puzzle as the impossible galaxies problem, because these objects appeared to have grown up far too fast, like toddlers showing up to school with fully developed careers, and the little red dots slot directly into this same uncomfortable puzzle. If they really are supermassive black holes forming within the first few 100 million years of cosmic history, then something must have kick-started their growth almost immediately after the Big Bang. Normal star collapse black holes start small, just a few times the mass of our sun, and need enormous amounts of time to grow into the billion solar mass giants we see at galaxy centers today. But if direct collapse black holes are real, some of these monsters may have been born already massive, skipping the slow buildup entirely. That is a fundamentally different origin story for the most powerful objects in the universe, and it is one that current models were not built to explain. Why does any of this matter to someone who isn't an astrophysicist? Because cosmology isn't just an abstract academic puzzle. It's the framework that tells us how everything, galaxies, stars, planets, even the atoms in our own bodies, came to exist. When a well-tested model starts producing results it cannot account for, scientists don't just shrug it off. They start asking whether something deeper is wrong. Is our understanding of gravity incomplete in the early universe? Is dark matter behaving differently than we assumed? Or is there a piece of physics we haven't even discovered yet, quietly shaping the first several 100 million years of cosmic history? Nobody knows the answer yet. And that uncertainty, at the frontier of one of humanity's most fundamental questions, is part of why the story has spread so quickly this year. Now, while all of that has been unfolding in the deepest images of the universe, Webb has also been busy much closer to home, in ways that briefly made headlines for an entirely different reason: planetary safety. In 2024, astronomers discovered a near-Earth asteroid called 2024 YR4. For a short, tense period in early 2025, its impact odds with Earth actually climbed high enough to earn attention from planetary defense teams worldwide before Earth impact was ruled out. But then a new question emerged. Could it hit the moon instead? By mid-2025, Webb's infrared observations had helped it refine the asteroid's size to somewhere between 174 and 220 feet, roughly the size of a 10-story building, and its lunar impact probability had actually risen slightly to around 4.3%. For a while, some astronomers were almost hoping to witness a real, observable lunar impact, a rare chance to study a crater forming in real time. Then, in February and March of 2026, Webb was used again in a rare, specially approved observation window to track the asteroid one more time before it disappeared from view until 2028. The result? NASA and ESA jointly confirmed that 2024 YR4 will not strike the moon. It will pass safely by at a distance of more than 20,000 kilometers. Crisis avoided, but only because Webb was there to close the gap in our knowledge that ground telescopes physically could not. It is a strong reminder that the same telescope unraveling mysteries about the dawn of the universe is also quietly standing guard closer to home. But the story that has genuinely rattled scientists this year isn't about asteroids. It's about a planet more than 100 light years away, and a chemical signature that keeps refusing to fully disappear or fully confirm itself. Because buried inside Webb's spectroscopic data of a distant ocean world, there is a molecule that, on Earth, is produced almost exclusively by living organisms. And the debate over what that signal actually means has become one of the most contentious, most emotionally charged arguments in modern science, precisely because nobody wants to get the biggest question in human history wrong. That's where we're headed next, because to understand why this single distant world has scientists more divided than almost anything else Webb has found, you need to understand exactly what was detected, how confident scientists actually are, and why that confidence keeps hovering just below the line that would let anyone call it proof. Now let's talk about the planet that briefly made half the internet believe we might have found alien life. Its name is K2-18b, a sub-Neptune-sized world sitting about 124 light years away, orbiting a small red dwarf star. It first grabbed global attention back in 2023, when Webb detected methane and carbon dioxide in its atmosphere, hints consistent with what scientists call a Hycean world, a planet with a thick hydrogen atmosphere sitting above what could be a warm global ocean. That alone was exciting. But then, in April of 2025, came the announcement that genuinely electrified the scientific community. Researchers led by astronomer Niku Madhusudan at Cambridge reported a possible detection of dimethyl sulfide, or DMS, a gas that on Earth is produced almost exclusively by marine organisms like phytoplankton. No non-biological process reliably produces it in large quantities. If it was really there in the amounts described, it would be one of the strongest hints of extraterrestrial biological activity ever recorded. For a few weeks, it felt like the biggest science story of the decade. Then, as is supposed to happen in real science, the scrutiny began, and it came from every direction. A team at the University of Chicago pointed out that other, far more mundane molecules, like ethane, could explain the same spectral wobble in the data. Independent groups reanalyzed the same raw Webb observations and consistently found no statistically significant evidence for DMS at all. One widely cited reanalysis confirmed methane at high confidence, but found nothing solid behind the biosignature claim. A separate joint analysis combining 3 of Webb's instruments, NIRISS, NIRSPEC, and MIRI, concluded that the supposed DMS signal was likely explainable by ordinary molecular features and background noise rather than any exotic sulfur compound. And then, on July 16th of this year, a new NASA-led study added what might be the most sobering verdict yet. While it confirmed K2-18b really does have a complex water-rich atmosphere, it found no conclusive evidence of DMS whatsoever. So where does that leave us? Not with proof of life, not with total dismissal either. It leaves us in the uncomfortable, honest middle ground that real frontier science actually lives in. As one astronomer studying the planet put it, finding life beyond Earth is the ultimate goal of the entire field. But that goal demands robust proof, not excitement-driven assumptions. That tension between the desire for a history-making discovery and the discipline required to actually confirm one is exactly why this story keeps resurfacing every few months instead of quietly disappearing. Webb will continue observing K2-18b. More data is coming, and somewhere in that data may be the answer that finally settles the debate, one way or the other. But here's what ties all 3 of these stories together: the little red dots, the impossible galaxies, and the K2-18b biosignature debate. In every single case, Webb did exactly what it was engineered to do. It pushed human observation past the edge of what our current theories could comfortably explain. It did not break physics. It broke our confidence that we already understood physics well enough. And that distinction matters, because it is the difference between science fiction panic and something far more interesting: the slow, uncomfortable process of watching our best models get stress-tested in real time. This is also why Webb's return to studying the edges of our own solar system has felt so oddly reassuring by comparison. When astronomers spotted the interstellar visitor known as Comet 3I Atlas moving through our solar system last year, Webb was one of the instruments turned toward it, using its near-infrared spectrograph to study a chemical composition that formed around an entirely different star, light years away, long before it ever wandered into our neighborhood. It is a genuinely wild thought. A chunk of another solar system drifting past our own gets its molecular structure decoded by a telescope built to look back toward the beginning of time. And when the asteroid 2024 YR4 briefly threatened the Moon, it was that same telescope, repurposed on short notice with special directors' discretionary time, that closed the uncertainty gap and ruled the danger out for good in March of this year. Webb, in other words, is not just staring at galaxies from billions of years ago. It is simultaneously functioning as an early warning system for our own solar system, and a forensic tool decoding visitors from other star systems entirely. So, when people say James Webb scared the world, what they really mean is this: it revealed how much of our confidence in the universe's timeline, the growth of black holes, the formation of galaxies, even the search for life itself, was built on assumptions that had never actually been tested against real observations this deep, this early, this far back in time. Now that Webb has tested them, some of those assumptions are holding up, others are cracking. And scientists, the people whose entire careers are built on understanding this stuff, are the ones sounding the most surprised. That leaves us with one final question, the one that should genuinely keep you thinking long after this video ends. If our best telescope, pointed at our best understood corner of cosmic history, is already producing results this strange, what happens as Webb keeps staring deeper? What happens when the next generation of space telescopes already being planned for the 2030s and 2040s, finally arrive? Are we approaching a genuine breakthrough in understanding the universe's earliest moments? Or are we standing at the edge of realizing how much we still don't understand at all? Let's step back for a moment and really sit with the scale of what's happening here. We are talking about a single telescope launched on Christmas Day in 2021, positioned nearly 1 million miles from Earth at a gravitational balance point called the second Lagrange point, cold enough and stable enough to detect infrared light from galaxies, whose light left them before our planet had finished forming. And in just a few years of operation, that telescope has produced not one, but 3 separate categories of results that are actively forcing scientists to question assumptions they had trusted for decades. That is an extraordinary track record for any scientific instrument in history. Most telescopes confirm what we already suspect. Webb keeps handing us puzzles instead. So what happens next? On the little red dots and impossible galaxies front, the honest answer is that we are still in the middle of the story. Multiple competing models, super Eddington black hole feeding, direct collapse black holes, and even exotic primordial stars are all still being tested against Webb's growing dataset. Every new observing cycle adds more little red dots to the catalog, and every added data point either strengthens one theory or weakens another. Scientists are not guessing randomly here. They are running detailed physical models, comparing predicted spectra to what Webb actually measures, and slowly narrowing the possibilities. It is entirely possible that within the next year or two, one of these explanations will pull decisively ahead. It is equally possible that the answer will turn out to be some combination none of the current models has proposed yet. Either way, the resolution of this mystery will directly reshape how textbooks describe the first billion years of the universe. On K2-18b, the pattern is likely to repeat what has already happened twice. An exciting signal, an eruption of public attention, followed by a slower, more careful process of independent verification that tempers the initial excitement. That is not a failure of science. It is science functioning exactly as it should. A single detection, especially one made at low statistical confidence in one of the hardest measurements astronomers have ever attempted, transiting starlight filtered through the thin atmosphere of a planet over 100 trillion miles away, is never supposed to be treated as final proof. Extraordinary claims really do require extraordinary evidence, and right now the evidence for life on K2-18b sits somewhere between intriguing and inconclusive. More observing time is already scheduled. The next round of data could push the needle firmly in either direction, and when it does, you can be certain it will dominate headlines again. And closer to home, Webb's role as an unexpected planetary defense asset is likely to expand rather than shrink. The success of the 2024 YR4 observations, using precious, competitively awarded telescope time to nail down an asteroid's future position well enough to rule out a lunar impact, has already demonstrated something planetary defense experts had only theorized about before, that a space-based infrared telescope can resolve dangerous uncertainty about near-Earth objects faster and more precisely than ground-based observatories ever could, especially for faint, small objects that vanish from view for years at a time. Expect Webb and its eventual successors to be called into service again the next time a newly discovered asteroid keeps astronomers up at night. Zoom out even further, and there's a bigger picture worth sitting with. NASA is already in the early planning stages for what comes after Webb, a mission currently referred to as the Habitable Worlds Observatory, aimed specifically at directly imaging Earth-like planets around other stars and searching for genuine, unambiguous signs of life, not through the indirect, statistically uncertain method of transit spectroscopy, but through direct light collected from the planet itself. That mission is still years, likely more than a decade, away from launch. But its entire existence is a direct response to what Webb has taught us this fast, that finding hints of something extraordinary is only the first step. Confirming it requires tools we haven't built yet. So was the world really scared by James Webb? Not in the way a disaster movie would have you believe. Nothing detected out there is coming for us. The asteroid that once threatened the moon has been ruled out entirely. The little red dots are billions of light years away, relics from a universe that existed long before Earth did. And the debate over life on K2-18b remains exactly that, a debate, unresolved and ongoing. But in another sense, yes, something has been shaken. Not our safety, but our certainty. The confidence that we understood how galaxies grow, how black holes form, and how rare or common life might be in the universe has all taken a genuine hit this year. And for scientists who have spent entire careers building and testing these models, that kind of uncertainty is its own form of unsettling. If there is one lesson buried in all of this, it might be the same lesson Hubble first taught us decades ago when it stared into what looked like an empty patch of sky and found it saturated with galaxies. The universe does not get simpler the harder we look. It gets stranger, deeper, and more surprising every single time our instruments improve. Webb has proven that all over again. This time, not with emptiness turning into abundance, but with certainty turning into open questions. And if the pattern holds, whatever telescope comes after, Webb is going to shake our confidence in something we currently think we understand completely. So here's the real question to leave you with. Which mystery do you think gets solved first? The true nature of the little red dots, or the debate over life on K2-CTB? Drop your prediction in the comments, because in either case, we are likely to find out within the next couple of years. And when we do, you will want to be here for it. If this kind of deep, evidence-based look into what Webb is actually finding is something you want more of, consider subscribing, because this story is nowhere near finished, and neither are we.